Here you go. Everybody have a copy of this handout today? So I thought the class has grown a little bit. This is probably the final size of it. So I thought it'd be nice to know the other people in the class, or at least hear their names, once in a while, where they are. So I thought we'd just go around and, say our names and say what year you're in and what major or minor you are, and then everybody just know a little bit more about who's in the class. And that could be helpful when we have discussions or things where you run into each other, around campus or something like that. So do you want to go first?
Sure. I'm William Galvin. I'm a math major and a senior.
I'm Annie Ledoux. I'm a junior and a math and secondary ed double major.
I'm Hattie Wolzewski, senior, double major of statistics and psychology and a minor in sociology.
Should I go?
Sure.
I'm Vic. I'm a junior math major, poli-sci minor.
I'm Abby. I'm a data science and math double major, and I'm a junior.
I'm Emily. I'm a senior. I'm a math major with a statistics and environmental studies double minor.
I'm Ling, and I'm also senior and data science.
I'm Bolton. I'm a math major and senior.
I'm Jordan. I'm a junior statistics and accounting double major.
I'm Zach. I'm an econ major and math stats double minor.
I'm senior. My major is math, and I'm senior.
My name's Joey Infantino. I'm a junior, and I'm a psychology major, stats minor.
I'm Connor. I'm a sophomore, and I'm an engineering major.
Great. So it's nice to have you all here. There's a diversity in interests, physical sciences, math, social, behavioral sciences. So it's great to have the mix. Statistics for me has always been interesting in part because of the wide variety of applications and working with different people who have different problems. And some of it's mathematical theory, trying to figure things out. And then other parts of it is application, really getting to how are things measured, how are the studies designed, and so it benefits from involvement of a lot of different types of people. So great. So today we're going to talk about sampling distributions. So it's Wednesday. And in chapter 4, we talk about sampling distributions. So these are sampling distributions of statistics, of functions of our data, statistics, numerical summaries of the data that we have. And we've talked about, we've used the idea of some sampling distributions in a way because we've done the randomization distributions or the distributions of statistics under an assumed null hypothesis. We want to make this more general to look at how to, what probability distributions do we have for different statistics under different types of samples. Not necessarily connected to a null distribution, but just when we have a sample from a population. And then we'll use that to develop methods for statistical inference and in general study that. And so, but in general, we want to talk about what this is in the general case and how you would describe or quantify and go about presenting something on a sampling distribution that you'd be interested in. So if we have a random sample, so I'm going to try and switch a little bit here to a little bit thinner pen. Click that and I get a little bit thinner. Let X be a random sample. And so the X might be, think about a vector or collection. It might stand in for measurements on observations, x1, x2, x3, up to xn. the notation is going to be a little bit loose, that it could be just a single variable that we're measuring somehow. But maybe our data set is a bunch of variables together. We'll have statistics that summarize things together. We're going to let t be some statistic. The book writes it as a function, h of x. Let that denote a statistic. Right? And by statistics, we mean some numerical function of our data. The data. Right. And so the data value, some numerical functions of these x1, x2, right up to xn. The book just writes it in very short notation here. Right? This t, this statistic, can be thought of as a random variable, right? In the sense that we don't know its value. So the t is a random variable if our x's themselves are random or uncertain before we go out and collect our sample and measure it, right? So it's, each possible sample can produce a value of, so each possible sample, right, x produces a value of t. Right. And across all the different possible samples, there's a range of values of t. Some are more likely, some are more typical, some are more extreme. So we get that distribution. And so a probability distribution is the possible values you can have along with their chances, either expressed in terms of probabilities for discrete outcomes or kind of relative frequency, kind of a density curve or cumulative curve that would say something about the chances of different outcomes in different areas, right? So how do we describe, in general, how do you describe a probability distribution? Probability distribution. So probability distribution, right, are values and how likely they are. In the kind of loose sense things. If we wanted to describe a probability distribution from the probability class, for those of you that are taking it, how do we describe probability distributions? Remember any summaries we did? Oh, yes.
Like by the shape of the distribution?
Yeah, so shape, right? So there are shapes of distributions.
Skewness.
Yeah, shapes. Symmetry, skewness. Right. So for instance, right, so if we just have a general sample from the population, and we take adults and we look at heights or weights or test scores, we might have a little illustration that the say heights of randomly sampled adults, right, is represented by this, meaning that there's some kind of central value, and the sample, there's larger ones, and some people are taller, some people are shorter, but the general pattern, if you had a large sample, and made a histogram or illustrated, it would generally kind of follow this kind of bell-shaped thing. So biologically in the population, it's kind of some influences that make larger heights or make smaller heights kind of across the population are kind of balanced out, right? So it could be like that. If we look at income, right, it's not necessarily, like that. It can be some incomes are negative, right? So there could be something like that. It might be more skew, right? So that's just general shape, right? So we might look at graphs, histograms, box plots, other things to look at it, right? That describes some of the distribution because we see where the likely values are, what range, and so on. What were some numerical summaries? What do we call it? Mean,
Standard deviation.
mean, standard deviation, right? So we could look at, mean. This was doing this in my other class. It's kind of sensitive to moving fast. So mean or average of the random variable. In probability theory, we call it an expectation. It's either a summation of the values or an interval. We're not going to focus on finding those now, but there's just an average value, kind of like if you had a population, you have a population value. If you have a model that says this is the density, well, if it's symmetric, the mean's right in the middle. In this one, the mean is somewhere around here, that the larger values pull it away from the cluster of most of the points because they're so far out. Mean or average, standard deviation. Of the random variable. So something like spread of it, standard deviation of random variables, how spread out things are. Some populations, the heights will be measured in inches or centimeters, or if you have other small animals, right, they can be measured in millimeters, inches, much smaller scale. And so how spread out things are. Some countries would have much more skewness, much more variability in their incomes, and so any of these random variables would be described that way. And because the statistics, these t's, are random variables, we can use those, right? So we're going to use graphs, averages, and so on to describe those sampling distributions. Right? The sampling distributions might be skew, they might be symmetric. It's going to depend on what the values of x are, what statistic exactly we're doing. So there's a great deal of variety. Right? A lot of introductory books end up drawing most things as normal, or when you see a picture of some random values in the news, there's often a little bell-shaped curve that somebody draws, but a lot of data is not bell-shaped, and a lot of sampling distributions won't be either. And we'll want to deal with that when we come up with testing or inference procedures. There are some special cases, right? So a special random variable, I'm going to say it's a special random variable, but you could also say it's a special statistic, right? And that's going to be x bar, right? So 1 over n, the sum times the sum of the xi values, right? So add them up and then divide by the sample size, the arithmetic average. As a summary. So this sampling distribution of this one, we can say quite a bit about, right, explicitly. Right? So if each xi has mean mu, right? So that would occur if each xi is sampled from the same population, random sample from a population. Then it turns out that the expected value of the sample average is that same thing, same average. So take a big sample from some population, and our sample average statistic as a summary has the same average value. The sampling distribution is centered on the population mean, just like each individual xi's were. Right? If each xi has standard deviation, a little deviation there, right? And the xi's are independent, of each other, right? Then the standard deviation, well, then the thing called the variance of x bar is sigma squared over n, and the standard deviation of x bar, which is also called the standard error, is sigma divided by the square root of n. That is, this measure of spread, this measure of standard deviation, is divided by the square root of n. It becomes much smaller as you take averages of more things, right? And the independence is very important, right? If if you take a sample, you take all the adults in a household, and you're asking a question like, "What's your household income?" Well, if people have know how much income is or what they reported on taxes last year, they're going to report the same value, right? It's not independent. If you have other people that are in groups and somehow it's a value that's common to the group or dependent on the group, right? If you're taking school children that are in the same school or the same classroom, and you're asking them how much time do you spend on doing something in the classroom. Well, most of the children will spend a similar amount of time doing that, so they're not independent of one another. So you don't really have independent observations. The information you have is correlated, and so with the other observations. So if you get one classroom that spends, an extra half hour every day reading, then all the kids are going to give a high value of reading. On the other hand, some other classrooms that don't do any reading, right, will have a very low value, and so X bar will have more variability if the observations are more dependent on one another. Right? You can't have an opposite situation if you're asking two people in the same household how much time do you spend doing laundry or cleaning and or cooking or shopping or something, or taking care of kids, and there's a trade-off kind of in percent time or something like that, right? Then those things would be negatively correlated, right? And so you could have smaller variance, so it just won't be accurate. But if they're independent, if you have one with unrelated people, their values should not depend on each other, sampled from a population, then that goes down. The other thing that happens under these scenarios, particularly with the independence, is that the shape of the distribution of X bar, of X bar's probability distribution, should be the more bell-shaped than the probability distribution for xi. And I'm just gonna leave it there, right? So the shape of the X bar's distribution, right, is going to be more bell-shaped than the original xi. Right? So the original xi could have skewness. It could have some extreme values, it could have clusters, but once you start averaging things in, some of the large and small tend to cancel out, and on average you get something there. Right? And if n is very large, the bigger n gets, the closer this gets. It might not be a very fast effect, right? But after 30, 60, 120 observations, the shape of many things is quite bell-shaped. Is more bell-shaped, so that's kind of an informal way of saying it looks more like a Gaussian normal curve, right? That would be there, right? So the book looks at so if n is large, we'll say, and large really depends on the context. If the underlying x's were extremely skewed, right, then you look at like land areas of countries or counties. Well, there's many that are very, very small, and then there's some that are enormous, right? So that's extremely skewed. So if you're sampling counties or geographical places, and there are vastly different sizes, the underlying x's are extremely skewed. And averaging together even 40 or 50 of them will still show the impact of those extremes right in there. But if it is large in the context, then X bar is very close to bell-shaped for its probability distribution. And so that's going to influence how we do inference and what we can say about the likely values of the mean, about mu, given a sample. If we believe that the sampling distribution is bell-shaped, we're going to work with that. Right? The book examples presents a couple examples. One is assuming that the xi's are distributed as a uniformly between 0 and 1. Right? So it's using a little bit of lingo from probability to set that up. But what this one is meaning is that the values of x that you will possibly see when you measure an individual, right? It's saying they are uniformly distributed between 0 and 1. So this little curve is called a probability density curve. F of x uniform just means constant on the interval from 0 to 1. And there's no probability, no density, no likelihood at all otherwise, right, outside of that interval. So the random values you're going to get, if you made a histogram of them, it's going to be pretty flat. Right? Take 10,000 values, you're going to see a little wiggle. It's not going to be exactly flat within bins, but it's essentially equal chances for all those. Right? So this one starts out, average for this one, or mean, starts out as 1/2. Right? The standard deviation for a uniform is actually the square root of 1/12. Right, there's an analytical way to find that, but that's what it is. And the shape, right, is just plain flat, right? It's not bell-shaped, right? So that would describe that, right? And if we're taking x bar, right, as sample size n here. Independent observations. Right. The average of x bar, the expected of x bar is still going to be 1/2. You take a bunch of samples uniformly, you're still going to have an average of 1/2. The standard deviation of x bar, or also called the standard error, right? We'll mention why that's is 1/n times that, so you could put the n inside the square root. So it's going to get smaller and smaller, and as you get bigger and bigger samples, you're going to be very likely to be close to that. And the shape for n that's of any particular size. Now n of 2 will be more like a triangle, right? N of 3 and so on, it's something else. But the shape for n that's appreciably large is pretty much mostly bell-shaped. It is bounded. We're not going to get an average outside of the 0-1 range. We are going to stay inside of that. So it's going to be a bell-shaped, but a little restricted. So what we want to say the shape of this is as n gets big, the shape is the shape becomes increasingly like the bell-shaped normal curve, right? Kind of informally. So the book is using this example. So this is an example it wants to use where things are flat, and then it will transition as you get bigger and bigger samples to that, right? The second example they do is the x's, the individual measurements, are distributed as something called an exponential distribution with some parameter. What symbol do they use? I just have they do a mean equal to 15 here. The exponential is a certain probability distribution where the density function, so here's the values of x, and then the f of x, right, has a density that's decreasing. It's always positive. F of x, like 1 over beta e to the negative x over beta for x greater than 0, and it equals to 0 if x is less or equal to 0. This model, right, this probability distribution is often used to model waiting times, like how long does something happen. Right? And so if something happens generally pretty quickly, right, it's going to happen in there, but there's a chance you could wait for quite a long time. Right? This particular one, the expected value of the xi is beta, or 1 over beta. I think it's just beta, right? And it turns out that the variance of an xi is also beta, so the standard deviation of an xi is the square root of beta. Now, in terms of knowing these rules, you know, these results, you don't have to have these things memorized for this class. This class is not about deriving those things. That's done in probability, but we're pointing them out because these are characteristics of the underlying data that we're going to have. Right? And obviously the shape is decreasing as you go along. Right? So you have a sample like that. Again, if you take the averages, the average of many observations is on the average of that, or the expected value of that average is going to be the population value again. And the variance, the standard deviation of it, or the standard error, is going to go down. Right? And even in a case like this, where it's so skewed, it will eventually become more bell-shaped. Right? Right. I wanted to look at one different example. Both of these things are continuous, right, at random variables. So the time could be measured to arbitrary precision. Whether you measure to minutes or seconds, you might still kind of model the underlying process that way. And uniform, if it's something, when would uniform happen? Uniform is useful for generating random numbers and other things. There might not be all that much that happens that uses uniformly random within in nature, but there could be part of a model of how something happens in there. So an example I wanted to look at, say, xi keeps doing that, follows what's called a geometric random variable with some probability p. Right? So this one is going to be another example of a random variable. We're going to look at it in R. And so on the website for the class, just to emphasize getting things. So there's some lecture notes here for this one, right? And there's an R script, and you can't quite see. This is the symbol for the PDF file. So this thing here is the R script in there. That's this R script thing here. So if that's saved to a directory and I'm working there, right? If I just right-click on it, I can open it. So it's asking me to open with something, and the RStudio pops up. Right? If RStudio wasn't there, I could search for the application or look at other applications and start it with R. And you can tell it, I think I've told it to always open with R files. But anyway, I've already done that. That is there. Now another thing that I happen to have here was an R data set, right? This particular data set. One way I can give you some of the data sets or data sets that I have that we're going to use for things, right, is to load them into R, save it as an R data file, and then put it on Canvas. Right? So I didn't put this up there for that lecture, but I will in other times. Right? And so if you have that there, RStudio is open, and you right-click on it, you can open it with RStudio, right? And it will just ask you, yes, you want it in there. It will pop. I'd already done that. So then the data set just pops in there. And so if I've saved a data set, instead of having to read the CSV file or do something else, it's easy to transfer R objects back and forth and get those. Right? So let's say that some data that we're going to measure has a geometric distribution. So there's a little help file in R about about that. So let's make this big. So this geometric distribution, there's a few commands associated with it. So what a geometric distribution does is, again, it measures the time until something happens, right? But it's a discrete count, and then there are times you try it, or the number of things you examine until it comes, right? And it's characterized by having a constant probability of success on each try, right? So if you're shooting free throws in basketball, and you have a 50% chance of success each time, and you're going to keep how many times it's going to take until you get there. You're going to count the first one, 50% chance yes or no. If you miss, right, then you take another try, and then you record the time that it takes to get it. Right? And so this particular probabilities, it looks like the way it's doing this is it's recording the number of failures. You either record the full number of trials or the number of failures until before your first success. Right? So if you make the first basket, you've had 0 failures, and the probability if x is 0, the probability is just p. 1 minus p to the x. If x is 0, goes away, that's just 1, and it's just p. The probability of p that you get it on your first trial and you record 0 failures, right? 0 errors. On the other hand, if the chance that you don't get it on your first try is 1 minus p, right? And so if you have 1 failure and then 1 success, right, you're going to get 1 failure and then a success, and that's going to be the probability. So to write that a little bit in here, so the probability, there we are. The probability that our random variable x equals some value is given as p to 1 minus p to the x for the values x equals 0, 1, 2, etc. So the probability of success on each trial is p, and we stop doing this activity or counting at the first success. At the first success. Right? And we record, right, number of failures. And so these are the probabilities, works out the probability of no success. So x probability could either be 0, 1, 2, 3, etc. The probability that we get that outcome for a single trial was p. That's the success. And if we need 1 failure, it's 1 minus p times p. We also assume that the trials are independent of one another, and that p is constant, right? So it's not like you adjust how you're doing something to improve. Right, that's always a question in evaluating sports or high level of performance in some activities. What's the learning process of doing things? The chance, how would you get an x of 2? Well, you'd have to have 2 failures, which would give us a probability 1 minus p squared times p, 1 minus p cubed times p, and etc. And that's the random variable there. Involved in that one, right? So we're going to use that kind of as an example for looking at a simulation here. So where's R? There it is. So if this number 0 through 20, right, gives me the number 0 through 20. So this D geometry, this DGM, will give me those probabilities calculated for the numbers 0 through 20, when p is 1/5, right? So the probability is 1/5 of a success. And I'm going to round those to 4 decimals, because otherwise it's a bit much. So we start out with a 20% probability of success, and then because we're multiplying successively by numbers that are less than 1, it keeps going down, right? So the probability distribution, the probability, go down. So the chance that we would get out to have 20 failures before our first success, right, or 20 failures before our first success is pretty small, right? where we're more likely to have, a few, 1, 2, 3, 0, 1, up to about 8 failures or something like that before we get that. We could end up waiting a while before we actually get a success in there. Right? And we can plot that. So here's a plot. The basic plot would be this first part of this command. Right? It's going to plot the numbers 0 through 20 and that, so it would end up going down like that. Right? So the probability distribution, this one's pretty skewed, right? and it's discrete. The command, if you want to put little labels on these things, this axis here is actually the probability, the discrete probabilities that we have a certain value that's along there. And now, if we take a sample size of 10, what's the sampling distribution, the average, or other things, right? Or the average, right? So what we want to do is look at a sampling distribution. Now, if you want to just look at the geometric, right? If we wanted to simulate the geometrics, we could do a histogram. We could randomly generate geometrics, maybe 1,000 values, right? With a probability 1/5, right? And if we look at that histogram, it kind of is the same. Right? Maybe we'll do 10,000 values just to. There's a option for histograms. You can put things on a kind of relative scale, so it'll make it into kind of standardizing probabilities instead of the count. So it's kind of the same picture, but instead of frequency and how many out of 10,000, this is kind of the fraction out of 10,000 that are in there. And our first probability is about 0.2, but this is kind of combined a couple categories in there. So yeah, it's kind of sloping down like that. So if we wanted to study that of just a single measurement, we could generate 10,000 values. Right? But if we want to study the distribution based on a sample size 10, we need to generate 10 times as many values and group them according to samples. Right? So sample size 10, get our statistic. Sample size 10, get our statistic. And go through that 1,000 times. Right? So let's, so in using R, if there's certain things that I'm going to use over and over again, instead of typing the number, if I can type a symbol, then it's a little easier to, it's actually frankly a little easier to read, right? Because if you P, you know it's the proportion, right? You know that that's the proportion 0.5, and so on. I don't know, I find it easier to keep track of those symbols if I use names that really make sense to me. So let's say P equals 1.5, let's do sample sizes of 10. So we're going to pick 10 geometrics. And let's do it 10,000 times, so we're going to record the means this time. Right? So to save things, to save the data, right? I guess you wouldn't really have to save all the data, but I'm going to set up a little matrix here, right? And in that matrix is going to be n rows, or capital B rows, and n columns, so it's a 1,000 by 10 matrix. And I'm going to go through each of the rows, and then each of the columns, and in that spot, I'm going to put one random geometric value. This is one way to set it up. And then after I get my 10 here in one row, I'm going to take the averages of them, average of that row, and save that in the means value. And in the end, I'll have 10,000 means. I also have my entire data set that I wouldn't necessarily need to do. But let's go ahead and run all this stuff. And I run through, and this is the histogram of means, right, of size 10. Right. So how is that comparing to our, these are the individual values, one at a time, right? And these are the averages of 10s. Right? The average of both is about 5. It's a little hard to picture where this average is, but it's about 1 over the probability. And this one is also in here, about 5, I think. There's 2 ways of writing the geometric, so it might be more like 4 based on that. But in any case, we could even see that. One way to see what's going on, let's take the mean of just a random sample of geometric. Let's get 100,000 or 10,000 of them. That's 1/5. It's about 4. So this one happened, the mean's about 4. And so again, we're around 4. But we don't have this big bump at 0 and 1, right? Because at a sample size 10, yeah, you'll get some zeros and ones probably. 0, 1s, and 2s, but you're very likely to get some other numbers. When you average it together, it pulls it away, right? And you're unlikely to get everything above 10, right? So you're likely to get a few small values. You might get, an extra share of a few more big ones, right? And that will pull the average up. Maybe one of these you had to wait, to 25. You're just freakishly long. It could happen. I mean, after all, we need to generate 10,000 values to do this. But this is the distribution of X bars are in there, right? And that has some. So average. So we can take the mean of the means. Right? So this is averages of the 1,000 averages, and each of those averages is based on 10. Right? We can also look at the standard deviation of those averages. Right? So the standard deviation of the average is about 1.43. So it's getting smaller than it was before. So this was one way of doing things. You can actually do these loops in here. R has different ways of programming. And so if you can utilize, this is just kind of an aside about the code, right? So if you can utilize matrices and vectors, it can go much faster, right? So for instance, if I wanted to just set up data, if I can generate 1,000 times 10 geometrics from that same one, it does it independently every time. And I can immediately put them into a matrix with that number of rows and columns. Right? So instead of doing that loop through I and B, that double loop, that does it all, boom, and that's all the data. Right? There's a command called apply, which is made for matrices. Right? So things are arranged in a square matrix, and now I want to do something where I apply some command to every row. Right? I want to go across all the rows and do the means. And so this apply to this data set across the first dimension, which is the rows, calculate the mean. So it's going to store 1,000 means. And I don't need to do a loop. Anything, just simulation. As we look at a little more simulation, we'll try to be more efficient like that. So we don't need to do so many for loops.
Can you pull up what the data set looks like again?
This one?
Mm-hmm.
So this dash, right? So the first, say 5 rows of that are going to be 10 numbers. And so the mean of that, the first row is that, and the mean of the second row is mean of these is that. And so when I do the apply for the first row and take means.
The first dimension? Oh.
The first dimension, yeah.
Okay.
So it's this apply is meaning to it means preserve the first dimension.
So you put 2 would be column?
It would be taking average over the columns, right? So, but the main point is that we get to simulate the distribution, and it looks like that. The means, and then based on this, we can summarize the means. This is about an average of 4.06, standard deviation of 1.43. You could also, for a probability distribution, look at key tail areas, right? What's the lower 10% value? What's the upper 90% value? That's very important in distributions of health, children's weight, nutrition, poverty levels. Percentages are extremely important in describing the distribution. Same thing for this statistic. The 10th and 90th percentiles, 2.3, about 5.9 out there, so we can describe that. You can take the median value of the means, right? So the means are 10,000 or 1,000 different averages. What's the 50th percentile of those 10,000 averages? So it's kind of you're taking statistics of statistics. You do simulations, so it's just something to apply to. Right? But as you change the statistic, you're going to get a different sampling distribution. Right? So you can take the same sample, the same data sample. So this will right? The same data matrix here. And each one of these is one sample of a geometric. So there were 4 failures and then a success, and then 2 failures and a success, and the next time it was 1 failure and then a success. What's the maximum out of 10 trials for the number of failures? Right? So this row should report 9 as the maximum, and this row report 8, and this is 11, 19, there's a big one. Right? That was, so that's going to be the statistic. T in the books. What does that distribution look like? Well, we can use that apply function on that data set. Right? And so every row is going to take the maximum out of 10. Right? And here's the histogram of maximums. Right? It's kind of still skewed, right? But you do have a much larger tail up here. Right? Those 40, you have sample size 10. One of those values, at least in there, was 40. There are some that have pretty small maximums, so you do 10 trials, you can get 10 numbers that are below 4, below 3, so there are some quite small maximums that are in there. The range of maximum values, 3 to 37, so certainly that's not probably the entire possible range. I mean, theoretically, you could get 0 every single time, right? So. And then the maximum would be 0. And you could go on for 50 or 100, possibly. It would be very freaky to do it that long if there's a 1/5 probability every single time. So this sample, that might not be the entire possible range of the maximum in 10 trials, but most of them are going to be there. It might be a little bit wider. Particularly on the upper end, you might get a few very strange cases. But it gives you a pretty good idea of where it is. You could look at something like the 90th percentile. There's a quantile function in R. And so you can take the quantile of each. So the 90th quantile out of just 10 observations is like the 9th one in order. So you sort them. So it's not the maximum one, it's the one less. Right? This apply is smart in this way. The quantile needs an extra argument. So it knows that the 90th percentile is the. So it just works. It works nice. As you do more simulation, recent programming, you might see a few more examples like that. So that will store all 10,000 of those. Here's the. It doesn't look quite as right. Now this is the distribution of maximums. This is the 90th quantile, 90th percentiles. How do those compare?
Slightly less skewed.
Yeah. The 90th quantile is a little bit less skewed off to that side, I think, right? And it doesn't go up quite as high, right? Because 90th quantile should be less than or equal to the maximum. They could be the same, right? If you had 9 and 9, right? Then they'd be the same number, but most of the times it's just they're a different number. In fact, out of that 10,000, 1,000 times are all less than or equal to. Yeah, that has to be true. 98 times out of 1,000 they were the same in this simulation. What happens when n is 40 in this simulation, right?
So that's rows of length 40?
Mm-hmm. Yeah, right. So you're going to have 40 geometrics and average them together. So it's like having a large classroom or a couple of classrooms together doing something and counting how many times until success, right, for each one. And then taking the average of those 40. So in this code, right, so for instance, like this data, and if you put 40 here, right, B is the same, P is the same, this data, so we're going to make it, N is 40 now, do that same one, and apply the means. Now the histogram of means looks like this, right? So these are the means of 40. And so doing a larger simulation with more can be pretty fast, right? A lot of the setup is getting it the first time and then modifying it. So that was that one. I've overwritten things. Where's the other? This was the other histogram of means, right? This was 10. Ideally, I would have changed the label to make it easier to see. But this was the one, right? So let's. What are key features of this one? Well, average about 4 as before, right? Kind of a range of a little bit less than 2 up to 10, right? A little bit of skewness, right? So with 10, we get that spread up to about 10 and some skewness. Now this last one that I made, based on 40,
Seems like 7.
yeah, it's up to 7. It's not quite as variable, right? That's the square root of n. You know, it's 40 is twice, 4 times the size of 10 because of the square root.
Twice.
It's twice as narrow, right? So well, it's kind of a range of about 5 before 0 to 10. So it's something. It's almost twice as narrow, right? Maybe there's a little bit of skewness, but it's not as much. So it becomes closer to bell-shaped. And so that's the sampling distribution. And right. And you can do other things. So that's what you can do 40. You could do other simulations. So maybe we'll just you can get really any shape, and some of these results are still used. But any questions about this geometric example in the simulation?
So we'd have to know something about what we were studying to use this as a simulation.
Right, so if you wanted to simulate something for your actual data set, right, you might look at the data or know something about the pattern, right, maybe from the past or your current data set, probably, right? And if one of these models applied to it, you might do it that. We will do something where we just reuse the data. We'll just resample from the data that we have. So if our data itself is skewed, if we resample from it, it's like sampling from the population. It's something called bootstrap. Right? So we'll use that technique to sample from things we don't necessarily have an explicit model. Other times, when we want to study procedures and how well they work, study mathematical, statistical inference procedures, we might say, well, our data is fairly skewed. It kind of looks like an exponential, kind of looks like something. And so we might use one of these models to generate data because it looks pretty much like what we'd have. Or some of these things have parameters, like this p, right? We're going to have estimation. So maybe we have a sample of size, 10 or 40 and get one estimate of p. Well, we're going to think about making a confidence interval or doing a hypothesis test. If we want to see, well, how well does that perform? Is that an accurate way to do the procedures for inference? We might put our p hat in here and then simulate, because that's pretty close to our population. Right? And so that would give us some evidence about how it's going. So we can use simulation to study sampling distributions in a lot of contexts. Right? The last thing that's on that handout there, as kind of another one, is something called a beta distribution. Right? Beta has values between 0 and 1. And if you choose a particular, the values of alpha and beta are greater than 0, they affect the shape of the distribution. And just as a little study here, values of 1/3 and 1/2, right? For beta, produce a graph that's kind of high in terms of 1 and then a little bit higher over here. It produces a bimodal distribution. Meaning that there's two distinct peaks there. Right? The average of this one is 1/3 over 1/3 plus 1/2, whatever that would simplify. 2, so you multiply it by 6 on side, you get 2, and then 2 plus, we get 2/5, right? Looks like the average, right? If you multiply through. So the average is a little bit less than over there for data, right? Where in the world would you have a model like this fit anything in real life? Well, if you look at counties, percent people voting for the incumbent, or percent people voting for one party or the other, this might be a little bit extreme to do that, but there'd be some that would lean one way or lean the other, and if in areas that are polarized enough, you might have that difference. If you look at populations across counties, and you looked at, or cities, neighborhoods, and the percent of the residents who are in the majority race. Right, or no, that's always be bigger, but you know, of a certain racial ethnic group, right? So like percent African American, or percent Hispanic, or percent Caucasian, or percent something else. If it would be separated if there was racial segregation, you know, kind of self-imposed, you know, living, and communities that are primarily one race ethnic group than other communities that where they're just absent, and you would get this type of extremes, right? If you're sampling counties and looking at something like that, that might be a very simplistic, naive model about things, but there could be some scenarios where you're getting that extremes, right? But anyway, that's just another model. If the data like this, you know, the average here is 2/5. There's some standard deviation formula that I didn't compute. But you know, it's going to be less than 1 because all the values are between that and 1. It's probably going to be less than 1/4. You know, it's 0.1 or something like that. If I needed to simulate that, if I wanted to know what it is, back to R. Right. There's a help file for betas, shape 1, shape 2, and different things that are there. If you take 1,000 values from beta, that's what it looks like. If you wanted to see, right, so, you know, it doesn't, even if you didn't have the theory to say what the mean and standard deviation are, if you simulate enough from it, let's do 10,000 times just to be a little more precise. So the average is about 0.4, right? The standard deviation, I don't need that. Right? About 0.365. Oh, okay, that's the standard deviation. It's a little bit larger than I would have thought, but you know, I guess one reason that that's bigger than I was thinking is that it's everything's so extreme, right? So that it's just everything's kind of pulled apart, and that means more variability than a uniform, right? So anyway, that's what the individuals are. You could sample like an average of, say, a number of observations, right? So we could have our new data. Let's set it up as a matrix. We'll do R beta. Let's do, say, 8, sample the size 8. So we'll do 8,000. So the number of rows is 1,000. So the number of columns is 8. You really only need one of these two arguments, and it figures out based on the number of people. I didn't do that quite right. R beta, we need to give it the parameters, 1/3 and 1/2. And then we do the matrix out of that. And the end of that is, right, so now my data, the first 5 rows, oops. I didn't run it, that's why it's the old one, right. Now I have 8 numbers in a row, right. It kind of laps over row 1, and then row 1 repeats to the other parts. But they're decimals. Here's some small ones. These are all small. Oh, but here's a few big ones in that particular sample. So it's getting it's getting samples up here and samples here. And of course it's possible to get some in the middle, but they're more rare. Right? If we wanted to look at the mean by row, so 1,000 means when you take 8 observations, here's the histogram, and I keep doing that. Run it. It's based on 8. Kind of the high ones and the low ones balance each other out. And even with 8, you start the average kind of starts to look like that. Right? So that's some things about sampling distributions. Right? That we'll be looking at. The book mentions that there's 3 ways to figure out sampling distributions. So you have an underlying data structure, data model. You're going to sample a certain number of times, and you want to know, and you have a statistic average, maximum, minimum, quantile, and you want to know what's the sampling distribution, right? Well, one is to do some exact calculations. With permutations, we realized that we could enumerate all possibilities if it's a small sample size, full enumeration. Sometimes with probability theory, which is, the book is in 4.2. We're going to mostly skip that. We might come back and talk about one or two things. So if you wanted to look through that, it explain a little bit more of the notation and a few things they're mentioning. But we're not going to be doing that. If you do probability class, the 61 in the spring does more of that, figuring out how you transform random variables and make new ones and things like that. Simulation. We're going to use that a lot to study procedures. And so by the end of the course, I think you'll be pretty good at setting up some simulations and generating random numbers and doing some things with them. That's a skill that if you take it into physics or take it into engineering or take it into other areas of application could be useful, right? And then there are some approximations to sampling distributions. The main one that we'll talk about on Friday is central limit theorem. Right, central limit theorem, or CLT, right? So a major result from probability theory, we'll use it in practice. And so for things like the average, or differences of averages, and some other things, we can do some approximation. Eventually we'll have generalizations beyond the ordinary. One from introductory statistics, like ratios of averages and things like that. It uses a nice Taylor series expansion from calculus. So we'll have some other ways to do a few more things. But we'll use primarily simulation of this, and where it's relevant, we'll state a result and use that for some exact results. But mostly the simulation. All right, so if you haven't submitted the homework one, you have it. And for a couple of you that are just joining, I know that you're going to hand it in on Friday because you're just getting into the course, but otherwise you can. Thank you very much, and that's both of them. Okay, excellent. Thank you very much. Oh, okay. Okay. No, yeah, okay. Good. No, that's. I have some other people to ask, but I thought it'd be a nice fit if you wanted to do it. But I also kind of anticipated you'd be pretty busy. So
yeah. Sorry about that.
Yeah, it's not that much money or many hours. So.
Yeah.
Thank you. Yeah.
Oh,
yes.
Can I ask you a question?
Yes.
I not quite understand permutation test over here. I read about it, but over here, this is one of the examples.
Right.
But in this case, females is 15 and males is 15 also.
Right.
What if females is 15 and 14?
Then you could have 15 here, and you could have 14 here. And then there'd be 29, choose 15, or 29, choose 14, would be the same.
I get two numbers?
So you're going to get an average for the females and an average for the males. And so our statistic is going to be this difference, 0.93 between these two groups. So the question is, if we set up a null hypothesis, right? So the null hypothesis is that there's no difference between the groups. Females, males really are not different. Then it's just random which numbers ended up here and which numbers ended up there.
Yeah.
Just random chance. So we evaluate that null hypothesis through randomly mixing up the data. Or randomly permuting the data.
I'm a little bit confused.
Yeah. So if we have, in this case, there's 30 numbers in all.
Yeah.
Right? And we